Okay, recording started. Now I am sharing my screen. Good. You should be able to see it, and you should see now my web page. So let's go to Harbour Engineering. I just want to make a brief recap. Last time we discussed during the first two lectures about port planning and forcing estimation for harbor design. When we discussed forcing estimation, we focused on the estimation of wind forces, and we also focused on the estimation of forcing driven by waves and currents. Today, I want to move a little bit forward during the first 2 hours of lecturing with the assessment of wave forcing into harbors. And in particular, I would like to talk about harbor oscillations, which means resonance that may be induced within harbors by incoming waves. So waves that are getting from the ocean into the harbor may resonate with the frequency, the typical frequency of the harbor, the inherent frequency, and may generate, after resonance, oscillations that may increase in magnitude during time, therefore originating big waves within the harbor, which is something that, of course, we want to avoid. And after the first 2 hours of lectures, I am planning to make a practical exercise. So today I am also starting the exercises to compute wind forces over a vessel, over a ship, and mooring forces. I just want to anticipate that I am planning to teach now continuously up to about 4 p.m. and then I make a break from 4 to 4:15, and then I'll teach up to about 5:20. So I need to make a break between 4 and 4:15 because I need to attend just for a couple of minutes online meeting, another online meeting. Okay, very good. Now let's then click on harbor oscillations. This is a new lecture which I published today actually. And this is the lecture as usual that you have to study for the exam. Pay attention here, there is some math. It's not complicated, but this is something that may be the subject of questions at the exam. In order to teach this subject, I take the PowerPoint, which you can find at the end of the lecture. There is a PowerPoint that I just prepared. Let me open it. Okay, here we are. You should see the PowerPoint presentation. So, harbor oscillations. What are harbor oscillations? They are motions of the water body originated by waves with a long period. So, we are talking of something that usually happens when we have waves with long period coming from the ocean, from the sea into the harbor. And in fact, I mentioned resonance. We are concerned by the interaction and the reinforcing, the mutual reinforcing of waves entering into the harbor with waves reflected by the harbor heads. And so the sum of the incoming wave plus the reflected wave may generate this resonance, which then may cause these oscillations that whose amplitude may increase over time. Of course, we want to avoid this. We want to avoid the huge oscillation of the water level into harbors, and this is why we study this phenomenon. Usually there is local awareness of the exposure of an harbor to oscillations. But there is to say that this oscillation depend on several features of the harbor itself, several geometric and physical features that may cause a variability in the way the process develops, in the way oscillations develop. So it is indeed something that may repeat with the same behavior, with the same features, but there might be also occasionally situations which are determined, as I said, by several conditions that may be varying in time, like, for instance, friction of waves with the sea bottom. There might be conditions that may generate occasional and very infrequent extreme phenomena. So this is why the process is to be carefully considered, even if we don't have notice of significant oscillations that occurred in the past. Sometimes it happens that an oscillation occurs and it doesn't occur anymore for hundreds of years. So it is something that needs to be carefully monitored with a precautionary approach, because the consequences may be very relevant, may be very damaging. What I said that typically these phenomena are originated by wave swing with long period. So what is the order of magnitude of the period we are concerned by? Usually the periods that generate oscillations may range between 30 seconds, I'm talking about the wave period, and 10 minutes. So you see it is quite a huge range. Usually we are not concerned by waves with a very short period. Shorter than 30 seconds, because this is very unlikely generating these extreme oscillations. So I mentioned resonance, and in particular, resonance means that there is a coincidence, a similarity, even if not a rigid similarity, not a rigorous equivalence, but there is closeness between the period of the wave and what is called the Harbour characteristic period, which we will see how to estimate it. We will define it with more detail. I just would like to say that it is something that we can compute under simplifying assumptions. And basically, the period of the harbor, if it is very close to the period of the waves, causes the superimposition, the reinforcing, as I mentioned before, between the incoming waves and the reflected wave. So what is important to know in order to check if an harbor is likely to experience this problem, what we need to know is the typical wave period, which may also occasionally occur, and we need to know the harbor period. So if we see that there is a closeness between these two periods, then we have to be concerned. This phenomena, which I called oscillation, it's also referred to as harbor resonance, surging, harbor surging, and harbor seiching, or resonant oscillation. The term seiche, in particular, it's widely used, and it is widely used, and you can see that there is a link in my web pages. Let me go to it, which refers to a Wikipedia page where you can find also some pictures. Here is the link. It's a coastal wiki, actually. Actually, there are no pictures here, but you see that there is the definition, and it makes reference to resonance, and there is also an explanation, notes, which explain what are the generating mechanisms of this seiche. And I will discuss the originating mechanisms in detail in the lecture. So there is no need for now to look at this web page in detail. Okay, so sorry, I go back to here we are. Now, these are phenomena that have been known for a long time, and in fact, there are already reports of episodes of seiching in the Lake Constance in Switzerland already in 1549, so about 500 years ago. And also a record of observed oscillations was taken in 1730 in the Lake of Geneva. And there is a description of the seiche, which was provided by a person who witnessed them, who saw them, and they were defined as the rhythmic rocking motions that water bodies undergo after they have been disturbed and then sway back and forth as gravity and friction gradually restore them to the original undisturbed conditions. So there is this sway back and forth. So let's focus in detail of what is happening then. This may occur not only in lakes, not only in harbors, The seiches can occur also in lakes, canals, bays, and also along open sea coasts in particular situations. Of course, we are concerned by harbors, but in lakes, as I already mentioned, in the Lake of Constance and the Lake of Geneva, in lakes, they are indeed likely to occur. And in the lake, they may result, in lakes, they may result from a sudden change or a series of intermittent changes, also in atmospheric pressure or wind velocity. So if we start with an oscillating wind velocity, the oscillating wind velocity may originate waves which may be reflected by the coast and then may generate oscillation. There is always a reflection mechanism that is activating these oscillations. In canal, they may be triggered by adding or withdrawing large volumes of water, and or in canals, they may be activated by the passage of, by the movement of ships. In bays, also in harbors, they can be originated by swells entering from the open ocean through the mouth of the bay. And this is the case we will refer to. So swells entering from the open sea through the mouth of the harbor. Or in bays, in large bays, they can be originated also by changes in atmospheric pressure. This is not the case of harbors because the harbors have a limited extension generally, and therefore it's very unlikely that in harbors the oscillations are generated by changes in atmospheric pressure. The dominant mechanism of generation for harbors is the entrance of swells from the open ocean. And of course, in the open ocean, also seiches may occur, oscillations may occur by changes in atmospheric pressure, tsunamis, or winds. And of course, there is always a necessary condition for the origination of these seiches, which is the resonance. So the similarity between the period of the forcing and the natural period of the water body. Let's then focus on the period, which is the important feature, the natural period of the harbor or a water body in general. So what is the natural period? The natural period is the period of oscillation of the basin once a perturbation has been induced. So if you have a perturbation in the water level into a basin, you understand if you lower down the water level into a basin and then we release the forcing, the basin tends to re-establish the natural water level, and therefore there is an up and down. So there is a down which is imposed by a forcing, which for reaction generates an up. And so there is a fluctuation which is induced of the water level, which lasts with up and downs until friction and gravity restore the natural conditions. If you have an intermittent forcing acting on a basin, and therefore you have something pushing the water level down, and you imagine that this forcing is then released, you have the up of the water level, okay? And then the water level goes up and then comes back down. So the time that occurs between two consecutive downs is the period. Now, when you get the next down, if there is the forcing that is pushing down again, then there is the summation of the intermittent forcing to the fluctuation, natural fluctuation of the water body. So the sum of the two may generate forcing down that brings the water level at an even lower level. So if the forcing is intermittent and the period of the forcing is the same period of the up and downs in the basin, then these fluctuations may overlap, may add each other, therefore originating the resonance. Resonance doesn't occur only in a water body. It occurs anytime that we have a forcing, a rhythmical forcing that is acting over a physical body which has its own frequency of oscillation. For instance, a well-known case of resonance is given by the walk of the soldiers over a bridge. So the soldiers in their walking, usually they walk with the same pace. So basically they hit over the ground with the feet at the same time. So if they walk over a bridge and the bridge is forced by their feet hitting the asphalt, hitting the bridge itself, then this forcing over the bridge, which is occurring for many people at the same time, may generate an oscillation of the bridge, a fluctuation. And of course, the bridge has a natural period, has an inherent period of fluctuation. So if the frequency of the walk of the soldiers is the same is the same frequency of the natural oscillation of the bridge, there is the risk of resonance, which may bring the bridge to collapse. And in making this example, we refer to soldiers because they are used to walk with the same pace altogether. In fact, if you look at soldiers walking over a bridge, when they get over the bridge, they break their pace. So they break their rhythm to avoid the occurrence of forcing by several people working over the bridge with the same rhythm, with the same pace. Let me give to you an example of a natural basin, a water body, where it's not natural, it's in the lab, where there is a forcing, a wave generation induced with a period that is the same period of the pool in the lab, in order to generate seiches. Let me click on the video, it is very short. There is the link on my web pages, and let's have a look at it. Just 1 second, here it is. Okay, let's wait for the advertisement. And just 1 second, and let me just wait for the end of the ad. Sorry for that. You know, YouTube has this disadvantage. Actually, okay, here it is. Let me magnify it. You see, this is the pool in the lab. And now there is a wave generator that is starting to generate waves. And you may have a look at the wave generator. It's at the other end of the pool. You may have a look at the behavior of the waves. Now you see the waves are traveling towards us, toward the screen. And then there is the reflection by the wall. And you see here the oscillation that is growing up. You see the forcing remains the same, but do you see the amplitude of waves that is progressively increasing? In the lab, it is relatively easy to generate resonance because it's an environment with geometry that is very regular. And let's see, there is another part of it. And you see that now the waves are not moving anymore. They are standing. This is interesting. Sometimes there is a little movement, but in general, you see that the wave is standing. And now there is the wave maker, the wave generator that is off. And you see the standing waves. And the wave generator is off now. So you see that they are long lasting, even after, of course, they are not increasing in amplitude because there is no forcing anymore, but they are long lasting. And of course, they are long lasting here because there is reduced friction. But you understand that this is something a little bit concerning. Even after stopping the forcing, you see the continuation of this indeed significant perturbation. Now is dampening down a little bit because of the friction, of course. Let me see, I think it's not yet finished. Let's move forward a little bit. Now it's dampening down. Let's continue to watch because there are some other interesting views. I think, let me check. We can jump a little bit ahead. Now is weakening, and so we can stop the video. Good. Okay. Presentation again. Now, how to study this phenomena and how to be able to make prediction. So in order to design appropriate countermeasures for contrasting oscillations, for protecting harbors and moor the ships from oscillations, of course, we need to make predictions. And to make predictions of the amplitude of the waves, and in order to make a prediction, we usually use a mathematical model. So it's interesting to then have a look at the theory, the theory that allows us to make an analytical description of oscillations. And but this analytical description as I said before, needs to take into account several features of the harbor, and needs to take into account friction, and needs to take into account also friction with, as I said, friction with the sea bottom, but also needs to take into account any singularity in the geometry, because of course also the presence of ships makes the geometry articulated and variable in time, actually. And this is why I said the phenomenon is complicated to describe. Now, it is anyway possible to study this phenomenon with numerical models or analytical models. Numerical model means that the equations which describe the motion of the oscillations are analytically solved. A numerical model means that these equations are solved numerically. The numerical model is generally used when an analytical solution is impractical, and in particular, it is used when the geometry becomes complicated. So what I want to emphasize is that we have two avenues in order to study this phenomenon. One is the analytical model, and the other one is the numerical model. Given that the analytical model doesn't allow to resolve complex geometries, we will indeed focus on an analytical approach, but we will refer to a very simplified geometry. Why we refer to an analytical approach? We refer to an analytical approach because clearly it's simpler and allows us to gain a better understanding of the dynamics, of the functioning of this process. So let's refer to a very simple case of an open basin with regular and rectangular shape. What do I mean with water basin with regular and rectangular shape? Let me open a graphic blackboard. So 1 second, and let's take open note. Should be around here. OneNote, sorry. Open, and let's see if it is clean or if I need to clean it. 1 second, I think I need to clean it because these are notes from another lecture. So let me write here Harbour Engineering. Harbour Engineering, okay. So let me draw a very simple sketch of an open basin, rectangular one. So let me see. So this is, 1 second, okay, now it should work. This is typically an open basin. Sorry if it's not regular because I am drawing with ends. So this is an open basin. So here we have the sea with the waves entering into it. And this is the mouth of the harbor. It's the open end, and this is the head. I'm sorry, I don't have the pen, so I have to draw with the mouse. And so, as I said, this is the mouth. The entrance is also called the mouth, and this is the head. Let's suppose that the walls are rectilinear. Actually, they are not here, but let's suppose that they are rectilinear, meaning regular, and the shape is rectangular. And let's suppose that the waves are getting into the basin in a direction that is perpendicular to the wall of the head. Okay, so here we have the waves entering here, hitting the wall, and this is an angle of 90 degrees. Okay, this angle here is 90. Okay, the angle here. So it's perpendicular. Okay, This is a very simplified scheme. Now let me go back to the presentation and let's move forward. So let me give some definitions before we start with the analytical treatment. And some of them I already anticipated. So regarding the geometry of the harbor, we distinguish between the closed basin and an open basin. The closed basin is not in communication with a larger water body. An example of a closed basin is a lake or a canal, okay? An open basin is one that is in communication with a larger water body along at least part of one side. So if I go back to this sketch here, this is an open basin because on the left, in the mouth, I have a communication with the ocean. What is the result of the fact that the mouth is open? The result is that there is no reflection of waves. When the waves that are reflected, they come back and they are not reflected by the ocean. Okay, so this is the difference. In a closed basin, the wave would be reflected from both sides. Okay, perfect. And let me move forward with other definitions. Regarding the forcing, we distinguish between, first, free oscillations, oscillations that occur without external forcing, although some external forcing was applied earlier to initiate the oscillations. So if you remember the video that we just saw, we saw that at the beginning there was a forcing given by a wave generator, but then the wave generator stopped and remained just stopped. So no more forcing was imposed over the water body. And therefore, after the stop of the generator, we have what we call free oscillations in the tank. Okay. The counterpart of free oscillation is forced oscillations. Oscillations in response to external forcing. What's the difference? The difference is that when you have forced oscillation, the resonance may increase the amplitude of the oscillations themselves. Forced oscillation and free oscillations may combine, and for instance, seiches are originated as forced oscillation, but then they may continue for a long time as free oscillations, as we saw precisely in the video. Now, the set of seiche periods and associated seiche structures are a property of the Harbour basin and are independent of the external mechanism forcing the oscillation. So, on the other hand, the amplitude of the generated seiches strongly depend on the energy source that generates them. Okay. Okay. Now, definitions again. We identify the problem as a two-dimensional problem. Oscillations are independent of one horizontal dimension, and a three-dimensional problem. And oscillations vary in both horizontal dimensions. The scheme that I had here is a two-dimensional scheme because as we will see, the oscillations, the waves that are generated into the harbor, they develop along only one direction in space, only one horizontal direction, which is the direction from the left of the screen to the right of the screen. The wave, the generated wave, doesn't change along the other horizontal direction, the direction that comes from the top of the screen and goes to the bottom of the screen. There is no change of the wave behavior along that direction. So this is a 2D problem, okay? Note that some textbooks refer to the 2D problem as the 1D problem by adopting therefore a different definition. Here we consider that there are 3 dimensions in space, and therefore we defined as 3-dimensional oscillations those that vary in all the 3 directions. Of course, on the vertical direction, there is a change. There is a change, and we assume that the vertical direction is implicitly considered as one dimension where we have change. And then you have the 2 horizontal dimensions, and then if in the 2 horizontal dimensions there is one dimension where there is no change, we end up with 2 dimensions where there are changes. The third one, there is no change. And therefore, we say the problem is 2-dimensional. So if I see this one, there is the vertical direction from the top of the screen to the bottom of the screen with no change, but there is the horizontal direction, the other horizontal direction from the left of the screen and the right of the screen where we have change. There is also another direction in space, the direction that comes out from the screen where we have a change, because the wave goes up and down along that direction. And therefore, this is why we call it a 2D problem, okay? But I just wanted to say that in some textbooks, I found that the 2D problem, what we call here the 2D problem, is called, in other books, is called the 1D problem, just to make you familiar with definitions. Now, again, let's assume that the Harbour has rectangular shape, as I said, and constant depth. This is important because, as you know, wave propagation is influenced by the depth of the Harbour, in particular if the depth is small. And so we assume that is constant in order to have a propagation along the Harbour with the same behavior, with the same characteristics. And we assume also that the head of the Harbour is given by a vertical wall, and that the wave crest is aligned with the direction of the wall itself, the wall of the head. And so that we have a 2D problem. The wave dynamics is 2-dimensional, and the wave is reflected perpendicularly. We also assume that the wave is fully reflected, okay? Which is not always true. But of course, if we have a vertical wall with very limited friction, like we saw in the video in the lab, then we have a reflection that is almost full. In reality, you know, in reality, the wave crest is not aligned with the direction of the wall at the Harbour head. In reality, the wall is not perfectly regular, so the wall has an irregular geometry. In reality, we don't have a full reflection. But in order to study the problem, let's take this assumption, which is also conservative. It's conservative because actually the fact that we don't have a full reflection makes amplification, makes resonance less concerning, okay? Resonance doesn't occur fully if we don't have a full reflection. But to take a precautionary approach, let's assume that the reflection is full. We also assume that there is no damping of waves along the basin, so no friction. So what happens in such conditions then? The wave is reflected with full reflection. What does this mean? The wave is reflected by a wall, by a vertical wall, and the wave that is reflected back has the same phase of the incoming wave. This is the big difference, which we can see from the mouth to the head. In the head, we have full reflection, which means that the reflected wave has the same phase and opposite direction, and approximately the same amplitude as the incident wave. Actually, full reflection means same amplitude. So what happens when we then superimpose the incoming wave and the reflected wave? What happens is that basically, given that the phase is the same, the linear theory allows us to simply estimate the resulting wave, which is given by the sum of the two waves, the incoming one and the reflected one, by just summing the two amplitudes. So this means that I have to sum the incoming wave to the reflected wave. I just sum the perturbation given by the two waves. And given that the phase is the same, what happens is that when I have a crest in the incoming wave, I have also a crest in the reflected wave. And when I have a through, again, in the incoming wave, I have a through in the reflected wave. So a double crest means that the height, the elevation of the wave is doubled. And the same for the superimposition, the exact superimposition of the two through. It means that the wave goes down to a depth that is twice the depth of the incoming wave. So the two waves sum up. And they sum up because there is a reflection with the same phase. Let's show a graph here. And before we look at the math, let me see the graph. So what happens is that let's forget about the yellow wave for now. Imagine the screen, the figure without the yellow one. We have an incoming wave or incident wave, which is the blue one, which gets from the mouth, which is open on the left, which gets against the head, which is a wall on the right. And what happens is that the wave back, the reflected wave, is precisely equivalent, it's specular to the incoming one. So the resulting green wave is simply given by the wave, by a wave with the same period and twice amplitude. Okay, this is because the phase is preserved. So you see that the green wave indeed has an height that is twice the height of the incident wave. Okay, which is a bit concerning, of course. And we call the points where there is the crest and the points where the oscillation is max. We call them antinodes. And we call instead the points where the wave doesn't originate any oscillation, because it's the point where the incoming wave assumes a position that is precisely the position of the mean water level. So even the reflected wave assumes the same position. These points are called nodes. And if you think about this process, and we will see a movie in a few minutes, if you think of this process, the red wave is not changing, it's not moving, as I anticipated when we were looking at the video. So the position of the nodes and antinodes doesn't change in time. And the resulting wave is called a standing wave. Standing because it doesn't travel. Okay. Let me show an animation. Before I show the animation, what is the yellow wave? It's another drawing of the reflected and incident wave at different time. So if we go to half of the period, if you go to the time which corresponds to half of the period, the blue wave assumes the position of the yellow one. And therefore you get a crest where I had previously a through, and the opposite, a through where I had previously a crest. The resulting wave is not shown here. So the standing wave at time capital T half is not shown here. So in order to understand this figure, you just have to realize that the yellow wave is the same as the blue wave after half of the period. It's the same wave after half of the period. Now let's look at a movie so you better understand. Here you have the movie. Look on the right. On the right you see the incoming and reflected wave, and in red you see the resulting wave. So first of all, look at the fact that the blue wave and the red wave, they are and the green wave, the blue wave and the green wave are traveling. So in particular, we have the green wave traveling on the right, and the reflected wave is the blue one. The red wave is not traveling, is not moving. So you understand why it's called a standing wave. Okay. Now, this occurs because the wave is fully reflected. Of course, if you don't have full reflection, there is the process is smoothed, is dampened out. So you don't have the formation of a standing wave that is precisely twice the amplitude of the incoming wave. What is our concern here? You understand also that if when you get the forcing on the left, at the left you have the mouth of the harbor, and look at the fact that at the mouth there is still what you may consider a reflection, but at the mouth there is not an antinode, there is a node. Remember, I go back to the figure. The node is where you don't have any change in water level due to the superimposition of the two waves. The antinode is where you have the max fluctuation. Now, you can see from this figure that at the wall, at the head of the harbor, you have an antinode, okay, and which is also shown here. You see on the right, there is the head of the harbor, and there is an antinode, okay. You have the max of the a max in the fluctuation. In the mouth of the harbor, on the left, there is a node. And why there is a node instead of an antinode? Because at the mouth of the harbor, you have a reflection with opposite phase. And let's look now at the previous figure. Here, you see that there is the case on the left where the boundary is free to move and the wave is reflected with the same phase. So in blue and up you have the incident wave, and in red you have the reflected wave. They have the same phase, meaning that a through corresponds to a through, and crest corresponds to a crest. And this is called a free boundary, because indeed water can go up and down along the wall. Let's look at the right, okay, where there is a fixed boundary. What does this mean? That there is no movement at the end, like in the mouth, because in the mouth, if you ignore for a moment the forcing, let's assume that the forcing has stopped and the ocean is flat. What does this mean? It means that if the ocean is flat, there is a fixed boundary at the mouth of the harbor. The harbor cannot move the ocean up and down. So the harbor, the wave generated into the harbor needs to meet the ocean in a position that is fixed. And this originates a reflection which is given by a wave that is has the same amplitude but opposite phase. And if the phase is opposite, then a crest corresponds to a through, and the two waves cancel each other. Okay, and this is why here I go back to the position here. You see that on the left you have the standing wave that is fixed. Basically, it goes into the ocean at a fixed position. Okay, and this is the difference between the mouth and the head. Now, the problem may be that actually if the forcing continues and therefore from the ocean we still have an incoming wave, then the standing wave and the incoming wave superimpose again. And we are concerned when the forcing, the incoming forcing is such that we may have a through when also the standing wave has a through, which means that we may have resonance. We may have resonance. Of course, it is the coincidence takes place when you have the period of the incoming wave that is the same period of the oscillation into the basin. Okay, now let's look at the math of it, because we saw this figure. Let's there is one more figure, but let's forget it. Okay, and in mathematical terms we have just to write the standing wave WS here as the sum of the incoming wave plus the reflected wave. So you have WS that is given by WI plus WR. Let me just 1 second. Let me put these formulas in the graphic blackboard. Just 1 second. So I can make some notes on it, okay? And meanwhile, I understand that this is not an easy topic to explain, because you need some time to look at the figures and understand how it works. And if you have any question and if you have any suggestion on any way I can help you, just let me know, okay? I am fully willing to spend the time that is needed. Okay, let me see if I try to paste it. Okay, let me just delete this sketch here. Okay, good. Just 1 second. I need to enlarge it. Otherwise, you don't read anything. Okay, perfect. So here you have the standing wave, WS, which is given by the sum of the incoming wave plus the reflected wave. This is linear theory, okay? Nothing particular. Okay, we describe the incoming wave, perhaps with this formulation, through a cosine function. So basically, the incoming wave depends on the position and time, of course, depends on only one horizontal dimension, as we said, by following our assumption, and time. So for a given fixed position x, we have variability in time, and for a fixed time, we have variability along x, okay? And then we describe the wave by first putting the amplitude here, and the amplitude is given by the wave height divided by 2, as we know. And then amplitude multiplied by the cosine of 2 pi, and here we have the dependence on space and time. Okay, L here is the length of the arbor in the longitudinal direction. So if the arbor is rectangular, then L is the size of the longer dimension of the rectangle, and capital T is the period of the wave. Lowercase t is time varying, okay? So we describe here the incoming wave, and then the reflected wave, we said that it must have the same phase. So basically the same argument of the cosine function, same phase, and same amplitude. And therefore it is specular. It is the same expression. The only difference is that we call the height of the incoming wave with the symbol hi. The subscript is I. With the reflected wave, we change the subscript to R, but there are no other changes. Okay, now we assume that the hi is equal to hr, which is equal to half of the height of the standing wave. hs is the height of the standing wave, and it is twice the height of the incident wave. Okay, and therefore the resulting standing wave is here. It's very simple, but of course it is written in this way because we imposed the same phase. And we impose the same phase because we know that when a wave hits against a wall, there is a free boundary, and therefore the reflected wave has the same phase. This is the key point, and we have to understand and to fix in mind this difference. Okay, understand it and fix it in mind. It's the difference between the head of the arbor and the mouth of the arbor. Okay, good. Now, we already discussed this figure, okay, and this is the result of the previous analytical treatment. And you see that the analytical treatment is extremely easy in this case because of the simplifying assumptions that we took. And we already discussed this figure, difference between the head on the left and the mouth on the right. Good. And we already discussed this one. And then we have also this figure, which is also a swing. It's the wave generated by a swinging elastic segment, which is free at one boundary on the right and fixed at the other boundary on the left. And you see here again the superimposition of the two waves, and then the result, which is a standing wave. And again, you see that it's similar to the other figure. It's similar to this one. Okay, these are all open open public domain figures that I found on Wikimedia. Okay. A string, okay. The correct call, the correct, I said a segment, the correct term is a string. Now, you see again another example. So propagation of a wave along a string with a fixed end and a free end. Again, this is the same figure, which also shows the position of the nodes and antinodes. You can simulate this situation if you take a string and you fix the free end to a ring which is free to move along a vertical pole. So you may take a string with a ring on the end, and this ring is free to go up and down along a vertical pole, and then the other end is fixed. Okay, and you may also assume that the vertical pole is given by your arm that makes the string moving up and down. Okay, so you may take the string with your arm, with your hand, and then move up and down. Okay, with the other end that is fixed, and this is the resulting movement which may originate. And here also you see that they mark the position of nodes and antinodes. There are several figures because when I studied these phenomena, I found it quite difficult to understand what it means reflection, and what it means reflection from a free boundary and reflection from a fixed end. And I could understand completely the phenomena when I made some experiments, some direct experiments. So one nice thing is to go in the lab with the wave generator. Actually, we could try to make it because we have a facility in the laboratory in Bologna at the university. We have a pool with a wave generator. Actually, now the pool is equipped with dissipators at the walls, precisely because when we generate waves, we put dissipators when we want to avoid the generation of the standing wave. So we should neutralize the dissipators in order to generate a standing wave. And indeed, the reason, the concern originated by standing waves is precisely the reason why lab facilities need to be equipped with dissipators. When we installed the pool, at the beginning there was no dissipator and we couldn't use it, because if you generate waves without dissipator, then it is the waves get reflected and experiments are not possible. Or maybe if you want to make an experiment on the generation of standing waves, that's fine. But usually if you want to make an experiment with instead for instance, to study the erosion over coastal structures, you need to put a dissipator on the other end of the pool. Okay, now here I would say that these considerations were already covered but by my discussion. So in open basins, we observe an antinode at the harbor head because water is free to move up and down the wall. And conversely, at the harbor mouth, there is no propagation of the harbor waves to the open ocean, which of course is not conditioned by a small harbor. And this is why we necessarily observe a node there. In closed basins, we observe an antinode at both ends. Yeah, this is important to keep into account. If you have a closed basin, you get an antinode at both ends. So for instance, in the video that we saw, this is the situation that we could see when the wave generator stopped working. So basically, we got to a situation where we had two walls delimiting the basin, and this is why the standing wave was generated. Okay. Now, resonance occurs when the reflected wave and the incoming wave add to each other. Resonance occurs when, as I said before, the wave period is the same as the natural period of the basin. So if the crest of the incoming wave is adding to the crest of the standing wave, then the resulting amplitude is amplified, and upon reflection, the standing wave is also amplified, which at the next cycle is amplified again, and so forth. And clearly, when does this condition happen? When do we have the perfect superimposition of the incoming wave and the standing wave that results from after reflection? It depends on the time that is taken by the wave, by the standing wave, to go through the propagation of to go through the harbor. The standing wave is standing, but I mean, in order to generate the standing wave, you need the incoming wave to reach the harbor head and the reflected wave to go back. So let me go to the graphic blackboard. Oops, sorry. It's not the graphic blackboard. The graphic blackboard it's not here. Just 1 second. I think, okay, here it is. 1 second. And I cancel these notes here. And I draw again a rectangular basin. Just 1 second, because this version, I think it doesn't allow me to easily, let me see, no, to easily make a straight line. No. Oops, sorry. Let me check if I can find a shortcut. No, it looks like. 1 second. Give me 1 second, because I'm trying to understand.
No problem, Prof. We can wait.
Okay. I think I got it. Just 1 second. I think I got it. Okay. Let me do like this. Okay. Now. Okay. And here we are. Let me see if I can. Okay. Okay. So the incoming wave that is getting from here takes some time to reach the head. And then when it reaches the head, there is the reflected wave that goes back with the same period. And the superimposition of the two waves generates a standing wave, which is standing. It's like the crest is here and another crest is here, etc. So the standing wave is not moving, but it is forming as the red wave travels back to the head. So when the red wave arrives here, then the standing wave is fully formed. So what is the natural period of the basin? The natural period of the basin is proportional to the time that is taken by the incoming wave to reach the head here and the reflected wave to come back. So this is the total time taken by the wave to go back, forth and back. And this total time is proportional to the period of the standing wave. Depending on the number of crests, the period of the standing wave, depending on the number of the crest of the standing wave, is given by the total period divided by the number of the generated crests. So basically what we have to check is whether this time taken by the time of by the wave to go forth and back is divided by the number of crests is close to the period of the incoming wave. This is the check that we have to make. So let's go back to the presentation. In fact, already in 1828, Marian proposed a formula to estimate the natural period for closed and open rectangular basins. I see that here symbols are missing with length, and there is a missing L, and depth, there is a missing capital D. Okay. And this depth is, remember that we assumed that is constant along the basin under the assumption of absence of friction. So this is the formula to compute the natural period, as I said, which depends also on the number of nodes, lowercase n. I said before the number of crests, which is actually crests correspond for the standing wave at antinodes, but the number of crests is the same as the number of nodes. So basically, if you look at this formula, it is given by 2L. Look at the right-hand side, 2L, which is twice the length of the harbor, twice because the wave needs to go forth and back. So 2L divided by, you see that there is the square root of G is gravity, times the depth of the basin. And this is the wave celerity. This is the wave celerity. So if you divide the length of the basin of the harbor by the celerity of the wave, you obtain the time taken by the wave to go forth and back. And then if you divide by the number of nodes, you get the period of the standing wave. This is very simple. This formula was already proposed in 1828. So you see that indeed this was a problem that was already well known at that time. And again, it's very simple. he computed the distance, he divided the distance covered by the wave, 2L, by the wave celerity. And then this is the time taken by the wave to go back and forth. And then by dividing by the number of nodes, he got the period of the standing wave. Now, there is another question here. And of course, what we have to check here, we have to check if the period of the standing wave is the same period of the incoming wave. This is resonance. Okay, so you see that analytically the problem is not so complicated, and please remember this relationship because it is not difficult to remember it because it has a physical basis. So if you remember what is wave celerity, how to compute it, which is I think something that you studied several times, and you make a simple reasoning, you are able to derive very easily this relationship. And again, we have to check if there is correspondence between the wave period and the incoming wave period and the standing wave period. Now, there is a question here. What is the number of nodes that I have to assume? Of course, the number of nodes depends on the period of the incoming wave, because the standing wave is generated by an incoming wave that is reflected. And therefore, again, the period of the incoming wave depends on the period of the incoming wave determines the number of nodes. And therefore, it follows that we have to study the resonance for different node numbers. We can assume first that n is equal to 1, and we see if there is coincidence between the wave period, incoming wave period, and the standing wave period with only one node. Only one node. We will see a figure in a moment. And then we have to make the same check for n equal 2, n equal 3, etc. by keeping in mind that the frequencies with the correspond to a high number of nodes are less concerning than the frequencies corresponding to a low number of nodes. So we don't have to make the check for an infinite number of nodes. When the number of nodes goes above 5, 6, that's okay. Then it's not so concerning. So let me look at this sketch here. And you see that for closed basins, there is only one node for the fundamental frequency. And there is what is called the fundamental frequency, the fundamental mode, okay? And for open-ended basins, you see again here, there is the fundamental mode that is given by only one node at the mouth, okay? So you can understand with only one node what is the period of the incoming wave that is concerning, okay? And then you increase the number of nodes for closed basins and for open-ended basins. You see in the middle row, you have two nodes for both cases, closed basin and open-ended. And then you can pass to three nodes, which is the third mode or third harmonic, okay? And the number of nodes is 3 in both cases, and so forth, okay, and so forth. So you have to make this check. I go back with the slide for, as I said, different number of nodes. Okay, now maybe that I can also prepare an exercise on that. I'll check. Maybe that during the break I have some time, or otherwise I can propose an exercise next time. Okay, now here, for open basins, we need to impose the presence of a node at the open end, and therefore the Marian formula reads in this way. And basically, you have to start from a number of nodes that is equal to 1, and therefore you can write the formula in the way you see here, because there is the multiplier 1 divided by 1 plus 2n. If you put there the n equal 1, you obtain 1/3, which multiplies 4L divided by GD, and the period for the fundamental node, n equal 1. 1 second, because I don't understand here. It's, I think, because I think it's the denominator is not 1 plus 2n, it's just 2n. I'll make a check, okay? But for now, let's assume that I think I made a mistake in writing, just in writing the formula. So basically here, we should eliminate. Let me just take this and put it on the, in order to provide the clarification. Just 1 second. I prefer to do this. Copy, and then I go over the graphic blackboard and I paste it. Okay, just 1 second. I can eliminate this sketch here, and then let's wait for the figure to come up. It's here. Okay. So I'll check, but my feeling is that we have to remove this. So basically, let me see, 1, or it's 1 minus. I need to check, okay? Because even if I remove this, I think it doesn't work, because okay, anyway, what is precisely correct is this one. And I'll check after the break. I'll tell you what is the correct form. But the period for the fundamental node is this one, okay? With only one node. And let me check for this formulation here. I need to check what's wrong. Okay, now let's go back to the PowerPoint, and then let's make some final conclusions. So the Marian formula is very useful because it allows a quick and easy estimation of the period of a bay, and it can be used to get an order of magnitude of the period, like a rule of thumb. And it can be used for harbors, for lakes, and it can be used to check if we are in a condition that may be concerning. As I said, to get an order of magnitude, we need to check whether there might be a kind of correspondence between the natural period of the basin and the period of the incoming wave. And then if we see that indeed there is a reason of concern, and then we may move forward with a numerical simulation. And here there are some examples of people that used indeed Marian's formula successfully. Torade found that Marian's estimate should be increased by about 10%, which is okay, if the width of the bay is about 1/10 of its length. If the width of the bay is comparable to the length, then the estimate should be increased by 32%. In general, these are corrections that were suggested for extreme situations. So if the bay is very elongated, is very, let me say, very rectangular, then Merriam's formula probably leads to an underestimation of about 10%, which is fine, because when we apply empirical formulas, 10% is an order of magnitude of the error that is fully tolerable. And instead, for basins where the two dimensions, the width of the bay and the length, if they are comparable, then indeed the underestimation is significant. It's about 30%. So basically, but what was found by other authors, and with respect to more precise computation, is that in general there is overestimation. In general, there is overestimation, and meaning overestimation unless the shape of the bay is almost squared, almost with the width that is comparable to the length of the bay. So unless these two dimensions are comparable, usually Merriam's formula is conservative, is precautionary. So let me give another example. For the Lake Superior, in one of the Great Lakes of the United States, the first mode, the estimate for the first mode for the period corresponding to the first mode provided by Merriam's formula is about 9.45 hours. And numerical computation instead gives a little bit more than 7 hours. For the Lake Michigan, the Merriam's estimate is about 10.5 hours against a numerical estimate of about 9 hours. So you see that for these natural lakes, the Merriam's formula provides satisfactory estimates. And I would say that for an empirical formula, these errors are really, really tolerable, the performances are really satisfactory. And indeed, this proves that this is a useful approach. Let's focus again on Merriam's formula here. So basically, let's keep it in mind. This one is for sure correct. And then, as I said, I need to give you some more details about this formulation here, okay? Now, the presentation is finished. Let me go back to the web page, because there are some final considerations that I wanted to discuss with you. Let me go at the end of the lecture. Here you see there are some references which should be, some of them are available on the web as open documents, not all of them actually. These references allow you to understand the fundamentals of this theory. And the final considerations, the very final one that I wanted to make is related to the conditions that the conditions where we should be concerned about Harbour oscillations. First of all, keep in mind that Harbour oscillations can really damage moored ships, can really provide a significant damage, because the standing wave may assume an amplitude that is very significant, which means huge oscillation also for ships, which means in turn implies an amplification of the mooring forces. An amplification because, of course, you understand that when there is a condition given by a standing wave with a high amplitude, then the ships may easily break also the mooring lines. And also keep in mind that this situation typically occur when you have a large harbor, which may host large ships. And if you have large harbors, because as I said, we are concerned by waves with a long period, up to 10 minutes. And we are concerned when this period is the same, is corresponding to one of the frequency of the natural basin, one of the frequency of the harbor. And therefore, if the harbor is very small, these frequencies have a period, even with only one node. Even if we refer only to the fundamental node, the period is very short. So we are more concerned for large harbors. And large harbors, as I said, typically host large ships. And ships have also their natural frequency of oscillation. It means that when the ship is subjected to a standing wave, also the ship tends to go up and down in the sea, in the water, with its own period. And we may get at the end of the story also a resonance between the standing wave period and the ship's natural oscillation period, which is complicating even more the situation. So we have to be concerned in large harbors. We have to be concerned when the tonnage of the ship becomes important, because of course we have less problems if we have only small ships that are moored. And we have to be concerned when the period of the incoming wave that we may expect is very long. I said in the range 10 seconds, 10 minutes, but actually it's the period it's a period ranging from more than 2 minutes to 10 minutes that is concerning. If we have a wave dynamics, if we have wave weather that does show frequently the occurrence of waves with long period, the problem is not really relevant. And for instance, if we have, for instance, the case of small canals, of water bodies where the oscillation period cannot be very long, this is not really concerning. What is concerning is, as I said, the superimposition of wave with long periods incoming into harbors which have a significant size. Okay, I would say that for now, let me check if there is something that I forgot to say, but I don't think so. Everything can be found in the web page. The only thing that I have to add when we start back with an exercise, but before then that, I want to check the question mark that I left open. Okay, I think we are okay here. Do you have any question before we make the break?
No, Prof, thank you so much. Everything is clear.
Okay, very good. Okay, now let me given that we can make a break of 15 minutes, given that, as I mentioned to you, I needed to make another call, I am stopping the video and closing this team session, and then I will reopen it in about 15 minutes. So you will have to get into the virtual room again. Is it this clear?
Okay. I come back at 4:15.
Okay, thank you very much. See you later.
Thank you so
Bye-bye.
much. Bye.